Well, now it's the last session of the week, and it'll be the best session of the week. We've got papers from the sublime to the ridiculous, and which is which depends on your predilections and point of view. First of all, we've got Walter Bertoldi, who's going to tell us all about the way vegetation rules the fluvial world. Walter.
Thank you, Mike. Good afternoon, and welcome to this last session, where I'm very honored to play the opening act. So my talk is about physical and numerical modeling of wood and vegetation, and I prepared this talk in collaboration with Virginia, that is here with us. And we will present a few different works that we have done in the recent years. And these works have been possible thanks to the collaboration of many other people who contribute in different projects. And I would like to mention only one person, that is Angela Garnell, who introduced me in the world of wood and vegetation almost 10 years ago. So in my talk, I will speak about both physical and numerical modeling. This is not so common. So I will start with what I think about models. That is basically that all models, physical and numerical models, are wrong, but some are useful. So following this famous quote by George Box. And there are many ways, I think, in which a model can be useful. I particularly like one that follows what Chris Paola and co-authors said in 2009, so that a model, they were referring to experiments, but I think this applies to numerical models as well, do not need to be a scale model of a natural system. But I think that they are particularly useful when they help understand processes, because you can do that in a controlled environment. So most of the experiments I will show you today refers to this kind of models. So where we are not looking at perfectly reproducing a prototype, but we are trying to understand some physics. So the outline of the talk is divided in 3 parts. So since there aren't many papers addressing at the same time wood and vegetation, these two are obviously linked. But as I will show you, it's not so easy to link them. So in the first part, I will talk about modeling vegetation. In the second part, about modeling wood. And then I will show you an example where we try to build a physical model combining both wood and vegetation. So, first part. It's well known now that vegetation, plants, have a crucial role in the fluvial system. And they are one of the 3 main components. So there is water, there are sediments, and there is vegetation. And all these are linked with 2-way interactions. So there are many conceptual models, many field investigation of these interactions. In terms of models, there are also a lot of models, but usually models consider only one of the 2 ways of the interaction. So there are numerical models that consider the effect of vegetation on flow and sediments, and we have seen one just in the previous section by Hiroshi. There are other models that look more at the vegetation side, and so look at how vegetation responds to changes in morphology or hydraulics. So I will come to this later in a minute. But first, I would like to discuss with you some new parameters that you have to consider when you build a model that want to look at vegetation in a more complete way. So already 15 years ago, I think it was at the Gravel Bed Rivers Conference in New Zealand, Chris Paola introduced this parameter T star, that is the ratio in between the vegetation growth timescale and the channel reworking timescales as a fundamental parameter to study the effect of vegetation on rivers. But this is not enough in some way, and recently in this work by Belletti and co-authors, people start recognizing the need to consider the timing of floods, because in between floods, sediments are sleeping, they are freezed there. So for sediments, it doesn't matter if a flood happens after 2 years or after 10 years. But this is not the same for vegetation. So when the sediments are sleeping, vegetation is happily growing. So this can change what is the final result, the evolution of your river. We explored this a few years ago with Angela Garnell with a very simple model considering a sloping floodplain, where you consider the vegetation as an element that can grow, so responds to water availability as a function of the groundwater level, and vegetation can be eroded by floods. I will not go into the details with equation. We already had a lot of equations today. But if you run a sequence of random floods on a system like this, in a certain environments, particularly in low pressure environments, I'm thinking about something like the Chalk Stream in the UK, for who they knows. So the flow is not varying a lot. You can compute single realizations of this random sequence of floods, and then you can compute an ensemble average. So the red line here is the ensemble average, and you see that the single realizations are not so different from the average. But if you change environment and you come here to Japan, for example, or in the Alps, where floods can be much stronger and also vegetation can grow much quickly, well, the average is not so different, but if you look at single runs, so real occurrences of floods, what you observe are distributions of vegetation that are completely different from the average. And this example is to stress the point that what you can see in the field always is, well, in most cases, is not the average, but it's a single realization, and this can really depend on the actual sequence of floods that you have. So coming back to the point of models, numerical models that consider the two-way effects of vegetation, last year with Nunzio Sevilla, we developed, and other colleagues, we developed a model starting from basement, that is the 2D shallow water model developed at ETH in Zurich. So we introduced a new module that considered vegetation in what we think a more complete way. So vegetation enters both because it affects the flow field through roughness. It also affects sediment transport through cohesion of the sediments, so the root cohesion. But on the other side, vegetation is also affected by the groundwater level, so vegetation grows, and grows not at the same way everywhere in the computational domain, and vegetation then can be eroded by the flood, of course. So one of the specific points of this model is, well, vegetation grows in time, and this we have seen also in the previous model by Hiroshi. But vegetation grows also in a different way depending on the groundwater and the bed morphology. So we can have different distribution. This is the bed elevation. This is the vegetation biomass distribution. You can have the on-off vegetation, the yellow line, step line. So under a certain bed elevation, you don't have vegetation. Above that, you have vegetation. Or you can have something that is distributed in a more complex way with a bell-shaped distribution. And in this way, you can model different species. So species that are very picky, so they choose a specific location, others that are more spread on your gravel bars. And the result can be quite different. So we investigated the case, a simple case, of alternate bars in a straight channel. So this at the top here is the bed morphology, the starting bed morphology. You can have vegetation in very different locations depending on the parameters of the spatial distribution that I showed you before. So there can be vegetation that stays on top of bars or vegetation that grows along the margins of the channel. Okay, so going to the results of the model, I will show you here an example of 4 floods. So we selected a very simple hydrographs. We tried to keep the model as simple as possible in order to be able to understand the effect, the controls of the vegetation parameters. So we kept all the rest quite simple. Sorry. I will show you an animation where you can see the evolution of the bed morphology and the evolution of the vegetation biomass. Just a caveat, you will see the vegetation growing instantaneously in between flood. This was to shorten this video, this movie, so we compressed the time in between floods in 1 hour here. So you will see the vegetation popping up. This is not in the model, it will grow in between floods, and you can decide how distant are in time the floods. So this is the animation. You see at the beginning, bars migrate downstream quite a lot, and there is very less vegetation that stays after the flood, but then vegetation grows again. And flood after flood, you see that the bed morphology changes. There is sediment deposition where there is vegetation, and bars migrate less and less. You will see in the last flood, they migrate only for a few meters, but there is quite a lot of deposition on top of bars where you have quite a lot of vegetation now. So this was just an example. You can play with the model looking at different types of vegetation. What we have found is that, well, of course, the final morphology is quite different. And if you look at the bed frequency distribution, you can see that they have a quite distinctive feature. So in the case of no vegetation, because there isn't, or because the flood removes the vegetation, the bed frequency distribution is negatively skewed. So the peak is towards the right. Whereas when the vegetation is present, the bed frequency distribution is picked toward the left, so it's positively skewed. So computing the skewness of the bed frequency distribution for many cases, we found out that if you change the discharge, or better, the unit stream power in your system, you find that there is a very sharp transition between the unvegetated condition and the vegetated conditions. So this means that if you include vegetation in your model, the system, in a way, flips from one state to the other. So there isn't an intermediate stable state. And so at the end, you can build a diagram like this, where you put the unit stream power on one axis and the ratio between the vegetation growing time and the distance between floods. And you find, well, depending on the type of vegetation that you consider, 2 areas where you have bare sediments or vegetated bars. And you can take your system, your river, and look where it is. And this could be useful, for example, if you change the discharge in your river because of dam construction or other impacts on the flow regime. You can see whether, if you are very close to the threshold, the system may go towards a completely different configuration. This observation on the skewness of the bed topography distribution has been observed also a few years ago on the Tagliamento River. That is my preferred field site in northern Italy. So we contrasted 2 different morphologies in a river that were in two reaches that are very close by. So the only difference was the presence or absence of vegetation. And in this case, you see that the bed frequency distribution is negatively skewed, and in this case is positively skewed. This use of bed frequency distribution becomes more common in the recent years. So also, for example, in this experimental work by Van Dijk and co-authors a few years ago, they studied the dispersion mechanism of vegetation. So this is another parameter that is relevant when you study vegetation. So you can consider that seeds are dispersed by wind, so you can find them everywhere, basically, like in this case. Or seeds may be distributed by water, so of course you find them on the margins of the channel. And this has a big impact on where vegetation grows. And as these authors pointed out, this can have an impact on the morphology, so on the bed frequency distribution of your river. Another thing that you can study with this model, and that has a good comparison with recent field and laboratory data measured by the group by Paolo Perona. You can look at where vegetation grows, for example, here as a function of the groundwater level, so going from the red dashed line to the green one, you decrease your groundwater level. Sorry, vice versa. You decrease going from 5 to 8. You see that vegetation grows more close to the channel because vegetation needs water to grow. But then when the flood is coming, also more vegetation is eroded. And this can have an impact, for example, on wood production. So I'm starting linking wood and vegetation slowly. So of course, eroded vegetation is what then becomes wood transported by UV. Okay, so going to wood, I will present some recent results of a model developed by Virginia, where it's possible to study wood. Because, as Hervé Piéguet said a couple of months ago at the Wood in World River Conference, wood is good. We all know that wood is good for habitat, but it moves. And when it moves, it can be quite dangerous. These are a few examples of recent floods that happened in Switzerland. And when wood moves during a flood, it can interact with structures, and we know that these are badly designed structures, as Colin Thorne pointed out yesterday. So there aren't many models dealing with floating wood. This that I present you is probably the first one doing it in a large-scale way. So this model takes origins from previous works made also by Gordon Grant here, studying when a log is moving, so the threshold for motion and how a log moves when transported by flow. So putting all this previous literature together, Virginia and co-authors, starting from another 2D shallow water model. This is Ebert, developed in the University of Catalonia in Barcelona. They added a module where wood is followed in a Lagrangian way, so each log is considered separately, and the model considered the fully dynamic model, so the full flow field on the cylinder, and so logs can rotate, they can float, they can roll if the flow depth is not enough for floating. They interact with each other, and they interact with the bank. So they can deposit on the bank, but they can also bounce on the bank. So I will show you, if it works, a video where you can see a few logs coming in from here and float downstream. Some are deposited, some then interacts with that. They can rotate. So it looks pretty nice. And with this model, then you can apply it to study what happens during a flood. And This has been done in an example of a large flood that happened in Spain a few years ago. And here it's exactly a badly designed bridge. So this area is the location of this study site. The model has been applied in different conditions, so you can change the number of logs you input, the dimensions of logs, and you can, at the end, study the impact on the flow depth and flow velocity, so you can study your structure and look at when it is at risk or not, and possibly how to solve problems. Of course, the model then can be calibrated and validated looking at field data. This is not an easy task because you cannot think that a model like this can reproduce exactly when the log is where the log is deposited. But of course, you can identify preferential sites for deposition. So the calibration is not so straightforward, but it is possible. So then the model has been applied also in other cases. This is a project with Polish colleagues on the Czarny Dunajec River in Poland. And this river gave the possibility to contrast two different morphologies. Again, so a single thread ridge that was relatively narrow, 30 meters, and a more multi-thread ridge, wider, 100 meters wide. So the use of the model can help understand, for example, the role of the diameter or the length of the log. And in this case, the model pointed out that there is actually a huge difference in these two morphologies, mainly because the response of these two morphology during a flood is quite different, because in a single thread river during a flood, you mainly have a change in depth, but the width is almost the same, whereas in a multi-thread river, the depth doesn't change much, but the width changes quite a lot. And the wood transport reflects this. And you can see that, for example, looking at the effect of length, in this case, the length has quite a big effect. So logs with different length going from 5 meters to 12.5 meters that are measured of logs that you can observe in this river. The transport ratio, so the amount of logs that exit the ridge compared to the amount of logs that you input, it varies quite a lot depending on length, whereas it doesn't in the multi-thread river, mainly because in this case, logs are smaller, much smaller than the width. So in this case, one of the relevant parameters is the ratio in between log length and channel width. When you are above a certain threshold, log length doesn't matter anymore. And this is nicely pointed out by this model. And I will come to this again at the end of my presentation. We observed this also in experiments, and we are now working on some comparison. So then, as you may have seen at the poster of Virginia here at the conference, you can use this model to study where logs may deposit more, well, there is a larger probability of wood deposition. You can do that changing discharge and looking at different morphological units. So you can see that the pattern can be quite different at different discharges, mainly because for higher discharges, the floodplain becomes active, so you will find a lot of wood in the floodplain, whereas at smaller discharges, you will find more wood in the islands inside the braided ridge. And this analysis can be quite relevant for river managers, because in this way, you can predict where wood is deposited and also how much wood can be deposited. And this can be relevant if you have a bridge downstream, as it was in this case. So you can see whether having vegetation is a good point because it stops wood coming from upstream, or whether having vegetation brings in more wood because, of course, eroded vegetation then becomes wood. So of course, it's not easy, but tools like this can help in finding a solution. So I will come now to the last part of my presentation, and I will try to link wood and vegetation. So this hasn't been done much frequently, particularly in modeling, because it's a really tough issue. So in order to couple eroded vegetation and large wood, you need a good model for bank erosion. But we discussed also previously, bank erosion is still a big challenge for numerical models. So if you don't have a good numerical model for bank erosion, you cannot model wood production. On the other side, well, there is always the other side of the coin. Deposited vegetation, deposited wood can resprout in certain environments, and they can become an island, a new island, so new vegetation. But of course, this needs understanding of biological processes, and this coupling is even more challenging than bank erosion. And this not for numerical modeling, also for physical models, because when you do physical modeling of wood and vegetation, most of the times you simplify your model quite a lot, particularly considering the biological part. So this is wood, this is vegetation, but okay, this vegetation is good if you want to model roughness, but of course not if you want to model biology of vegetation. Well, anyway, we had a crazy idea a few years ago with Luca Mao that was leading this Hydrolab project, and also other guys that are here in this room, Francesco and Michal. And we tried to do experiments in braided river with both vegetation and wood. It was great fun, but quite challenging. And also in this case, you see, we decided to reproduce wood and vegetation in a different way because it was not possible to do otherwise. So in the end, we were quite happy with the results. Here are a few comparisons of what you can see in the field and what we observed in the flume. So qualitatively, it looks nice. This is another example. So then we performed runs without vegetation, and we saw that wood is quite spread around in a very dynamic system. So you see all these small points, these are single logs. So in this case, wood is deposited mainly as single logs or small groups. This is because the system is very dynamic, so bars are changing position very rapidly. And not only, it's changing very rapidly, but anyway, the wood doesn't travel fast. Another results that we found from these experiments is that wood stops at the first bar. So as a colleague of mine said, it's like researchers, they stop at the first bar. So then we added vegetation, and things at the beginning were quite similar, but then you see vegetation starts to change the morphology, so you don't have any more a braided network, you are more a single wandering channel, and I hope you can see there are big jumps of wood growing, because in this case the system is not so dynamic, so wood deposits in the same preferential sites. In the end, we counted something like 400 or 500 logs in this jump here. So it's a completely different situation from the one before. And this summarizes the results of this work. You can see here in the case of unvegetated flume with low input rate, almost half of the logs are deposited as single logs. If you go on the other extreme, most of the logs were deposited on very big jumps. So I think my time is almost over, so I'm arriving at the end. This is what I anticipated you. We are now with Virginia trying to compare physical and laboratory models, physical and numerical models. And this, I think, it's a very powerful tool because both in physical and numerical models, you can do the same simplifying hypothesis. So if you look for data to calibrate and validate your model, if you have laboratory data, they can be exactly designed for your model, and this can help you quite a lot to understand what is working and what not in your model. So Okay, I will thank you for your attention, and I will wait for questions.
Thank you, Walter, for an excellent and excellently timed presentation. Well, now from vegetation all over the place, we're going to vegetation nowhere. And for vegetation nowhere, you've either got to go to the Atacama Desert, or the Silurian period, or another planet. Bill has been to the Atacama Desert, but I think he likes more exotic things. Not being able to get to the Silurian period, he's chosen to go to another planet. So what we're going to learn about now is a little bit about rivers on Mars.
And here we go. This is the film of the Curiosity rover landing. The camera's base is under that thing that's sent away was the heat shield. And what you're seeing here are dunes, very large dunes composed of olivine. And we're going to watch it land. I thought when I was looking back today, I thought I needed something I had to win the award for the ridiculous. So think about this. This is 225 million kilometers away. They created a landing ellipse that was 20 kilometers long, and they landed in it. And the design, which you'll see here, is a sky crane. That is, the thing came in with a heat shield, and it popped off the heat shield, and it uses jets. And it's going to slow itself down with jets, and then it's going to lower the rover down on cables. And the cables are going to disconnect, and the rover's going to drive away. And I have to tell you that I was one of the people who thought, this isn't going to work. But it worked. And here we come. This is not an animation. This is Mars. As you can see, there's no vegetation. And it's hit by a lot of craters of all sizes. Oop, here we go. There's the jets. And what do you see? Fluvial gravels. It's true. When we landed, we were shocked to see, ooh, something just happened to the color. There you go. And this is when the rover woke up and looked up. There are 17 cameras on this rover, and that's not Mount Fuji. That was Mount Sharp. Okay, that's the camera. Okay, stop that. That's Yosemite, which is the operating system, right? Come on, Steve Jobs. Okay. Oh, this is not going to be good if that's what happens to all my pictures. So, fluvial gravels on Mars is what I want to tell you about. It could also subtitle it, or what might fluvial gravel tell us about the climate history of Mars? We hold a particular position in helping to understand the evolution of Mars, strangely, by the way, things we can say about climate. My colleagues, all involved in the Curiosity rover mission, there's 400 people. This is a group that focused on the gravel some. Here is a slide that Gordon Grant showed in 2005 of questions he was asking. And he asked this question, are there gravel bed rivers on other planets? And he proposed that by 2025 GBR, we'd have the meeting there. We'll see if that happens, at least some of you might see. Okay, Mars. There it is, elevation map of Mars. The brief history of Mars, time scales, billions of years going this way, and general change in the mineralogy. Early Mars, there's clays that are produced. Later on, sulfate dominated and then oxidized. And look at these time scales. My colleague Alan Howard said you could think of it as the early epoch here when the circular depressions that are the relic of giant craters had been eroded away. It was clearly raining. It was clearly a substantial hydrologic cycle. But about 4 billion years ago, the the dynamics in Mars died, and the atmosphere blew away. And so there was a big change. And this has caused a trauma in climate modelers because even though it blew away, there's clear evidence of mid to late Noachian here activity of some crater degradation, and more importantly, what Alan calls a climatic optimum. Right around here, all sorts of fluvial activity was present, and then just spots after that. This is what these eroded edges of craters look like for that early period. Here's what channel networks look like coming together, or maybe possibly seepage channels. There's places all across Mars that have channel networks like this. This looks like any old landscape on Earth, with valleys going up to the divide. That looks like it evolved under a precipitation, and in a period that makes climate modelers uncomfortable. Fans, intersecting fans on the ground surface there. You can see the individual channels radiating out. This is what we whimsically call the pancake delta. You can see why. Those are impact craters. This is where we just landed, right about there. And based on that delta front, which is 100 meters high, the mean depth of water at that time was 650 meters. And this, here's another view slightly later that's recorded by a delta here, 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 and over here. That was 440 meters deep water. This is, in this one crater, we see there was a lot of water. But there's other evidence. Ebbswalder Delta, which was one of the landing sites considered here, you can see the different delta fronts. And if we look very carefully in here, we can see meanders with cutoff loops. A scale of meanders being about about 150 meters across, a mean slope of about 0.006, and it transported boulders. Fluvial processes, meandering on Mars, spectacular. Other examples. This is at first maybe seems strange to you. This is not pasta. These are inverted channels. So the idea is that these channels were carrying probably gravel, but they were overbanking fine-grained material. The winds came along much later and blew away the fine-grained material, etching out the inverted channels. Channel networks, meanders. Closer up, in this, you can also see the actual scroll bar complexes of these beautiful meanders on Mars. Sorry, but we don't have to have vegetation for meandering. At least we haven't found any yet. And there are also, some of you know about the great outburst floods. This is 4 kilometers across here that occurred in localized areas on Mars. And then most recently, in our research time and on Mars, are these small gullies that are known to be active. The repeat flying now for a decade across Mars shows that some of these gullies are actually changing. So Mars is still quivering. There's still a little bit of hydrologic activity taking place, even in most recent times. So let's go back to Mars. You probably all know about Opportunity and Spirit, where they were. These are the earlier missions. These were the competed sites, and Gale's right here, where you just saw the rover land. And it landed at a very interesting time, right at this transition in what might be sort of the end of the, quote, climatic optimum. So that presents an interesting circumstance, because this crater right here landed, the impact hit right at what's called the Great Dichotomy in Mars. And by that, there's a big elevation change across here. And it hit an observable channel network draining an area that was 270,000 square kilometers. Most likely, it hit when that channel system was active. So this crater hit, it created an impact with a very different height on either side. You can see in this colorized plot here or in this dipping plot. And in fact, the high point here is nearly 3 kilometers higher than the low point over here. And the total mountain is 5 kilometers high. And it is interpreted by the early researchers here, Mele and Edgett, that this crater once possibly was completely filled in with sediment and then was re-scoured out. And let's just say no one really knows if that's right or wrong, but we do know that the bulk of sediment around the center of the spike, bulk of material, is sediment. There's a central peak that looks like it's not sedimentary rock, but from bottom to top, there's sedimentary rocks. This is an early pre-landing view where this is the landing ellipse that they were shooting for. And then what was recognized was a sort of outline of a fan here with something different above and below. But importantly, from space using spectral imagery, it was recognized that there were very thick units of clay and sulfate. And as I've already shown you, that's a tempting story to explore because that might be the climatic history of Mars coming up, because after that, it's iron oxidized. So the reason in the end this site was chosen to land is because it seemed to possess a rich geologic history that might tell us about the climate history of Mars. But the other thing that was the mission, the singular mission of this of the rover, was to look for habitable environments. Not look for life, not try to find something creeping along, but just could we find all the elements necessary for life somewhere in our journey. Another view to show the contrasting material types. This is that thing was labeled a fan, and you can see contrasting materials that you can see due to thermal inertial imagery. So something very curious, bad choice of terms, very interesting was happening. We landed right there, and that's quite important where we landed. Here's the image, by the way. You saw the descent. This is a satellite picture of the descent. So it's coming down in a balloon, in a parachute. So it popped off the cover, then was brought down with a parachute, and then you heard the engine switch on, and it was lowered down on a crane. So there's the heat shield coming off the dunes I mentioned, and then the jets that were activated that blew away the material, actually exposing fluvial gravels. And there's the rover being lowered down, cables cut and drives away. Then here's the first photograph that returned, and a group of us were standing looking at the images, the very first image back. We looked at it and said, we landed on rounded gravels? This seemed like a surprise and an opportunity. And this is the first view back to Mount Sharp. Okay, so you see some blast marks here that helped us see exposed material there. There's Mount Sharp, a fairly desolate looking environment, I think you have to say. But strangely one that doesn't seem really too foreign in appearance. This is the rover. There are 10 major instruments on it. I've summarized the main ones here, which has all been clipped on this fit. I didn't catch this before. So there's something called ChemCam, which is basically a laser beam that then vaporizes materials, and the spectrometer uses that to get composition. This is a French-led team, and it's been a very powerful tool. There's a system for doing spectrometry to get total chemistry by taking samples using what's called APXX. Also cut off here is an instrument package that's called SAM that has I think it's 3 spectrometer that can do isotopes, do carbon composition, and in fact enabled us to do the first cosmogenic radionuclide dating of another planet. And then there was an X-ray machine, X-ray mineralogy, which landed here exactly 100 years to the day when that system was invented to do mineralogy. Here's a view out the back of the bus. And this is looking from the rover back toward the rim, where you see the rolling landscapes, and they're kind of rounded. And at least in my experience, that doesn't look very unfamiliar. It looks like, well, Arizona, New Mexico, a roundish sort of landscape there. Here is a map of where we landed. We landed at BR here. And what we saw early on, actually before we landed, we recognized that there was a fan here, and you can see very plainly from the contours how it bulges out. But what's interesting is it goes into a enclosed basin, this wide area of about 64 square kilometers, and we landed within that basin. Now the rover mission, when it landed, was to turn and go to Mount Sharp to get to those beautiful clays and sulfates. But we saw this. This is within the first 20 sols or Mars days. And let me take you a little bit closer, because these are strangely bleached looking as projected. A little bit closer. You can see 16 millimeter grains there, and this. These are bean-shaped particles, that rounded, that are composed of basalt, that are reasonably well sorted, sort of 4 to 9 millimeter median grain size. When we look at the exposed outcrop, we see evidence of sorting. We see grains resting on each other, and we see some vertical variation. Now, the first night when we got this picture, Jet Propulsion Lab is on a fan. So I went outside and brought gravel in and held it up to several hundred colleagues and said, is there any other method, any other process that can make this other than fluvial? This is really important because in the end, and if anybody has another idea, let me know. It's not glacial, it's not wind. I can't think of any other process that takes a broken piece of basalt and makes it into a beautifully rounded, sorted material that are weakly stratified in here. The reason I emphasize this interpretation, let me take it a little farther, is we can do some calculations because we interpret it as fluvial transport. We can use a critical Shields number. We can then solve for depth. We have an idea of the slope because we're actually on the edge of that fan, so we can use slope in here. And so we can calculate a shear stress and a shear velocity, and we can actually measure grain size, and so we can estimate the mean velocity, and this would be the mean velocity. Note that U star in it would have a shear stress, which would have a G term. G is 3.7 meters per second, so there's reduction of velocity by about 0.6. So we could calculate velocity right here, and the flow depth for the stream would have been about to here, we estimate. So we could calculate that there was a river flowing here. That river would look something like this. This is Chile, we think. And so what this said to us is that all those pictures I showed you before that showed deltas, that showed fans, that showed meandering channels, I have to tell you, many of my colleagues said, couldn't it be lava flows? Couldn't it be done by gas? Couldn't it be done by some other medium? And the reason for that is it demands water. And it demands, you're going to see, a lot of water. And many of my colleagues say, we can't do it. The climate modelers cannot produce the climate system that the geomorphology demands. So getting this message across, and if someone here has another idea on this, let me know, that this is fluvial gravel, forces us to confront that issue, and it validates 30 years of photogeology, saying we interpret this as a meander. I had a colleague who uses spectral imagery, and I was showing him the meander on the Eberswalder Delta, and he said, how do you know that's a meander? And I said, watch, shoe, I mean, it's a meander, right? But my spectral colleagues say, well, I've got this remote sensing device and I can get all this data and I can analyze it. I've learned since then that they can analyze it for years and still not agree what it means. So I'm projecting a certain point of view because we're amongst ourselves. But geomorphology on Mars is really important because it holds up a fist and say, you have to have water, fluvial processes, and I'm going to show you a fair amount. Now, another thing it did is going back to this, what I call my Easter egg map, these are contour lines, again, 5-meter contours. The high-rise imagery we have from Mars is 25 centimeter resolution. So we can make actually 1-meter contour maps here. But anyway, there's 5-meter contour maps. You can see it going into this enclosed basin. When we landed here, and we were supposed to turn and go this way, some of us stood up, and this is the slide I showed the first night, and said, we ought to go exactly the opposite direction, because if you're going to look for lake sediment, where would you go? You'd go into the enclosed basin at the base of an alluvial fan. The water would run past and collect in the basin and form a lake. And if you want to find something that's watery, that's a nice place to swim around in, that would be it. To my surprise, the people who run this show agreed. We spent 6 months getting over there because you go 30 meters and then you're frightened and you think, am I safe to drive on? Because you have this expensive machine. But we went there. But I also have to point this out. This is the Karube fan, where we're going tomorrow. And it is almost exactly the same slope. It is almost exactly the same surface area, and it drains almost exactly the same catchment area. It's the best analog I have found in looking around for a Peace Valleys fan in those criteria. So I had no idea you'd choose this as a field trip, but I'm very excited to see it. But think how different this is. I mean, okay, it doesn't have people on it, it doesn't have Sabo works, it doesn't have dams, and it doesn't rain this way. So that's a twist on the knob thinking, what exactly controls morphodynamics? if you have something that's this dissimilar in its origins, but it is going into a body of water, an ocean. So I put this up to chew on, to think about. And I'm very tempted by this because we see evidence of channels on that, on Peace Valley's fan. So we drove to the base of Peace Valley's fan, to the spot we said there ought to be lake sediments, and there they are, kilometer-long deposits. We drilled, and the first thing we discovered is Mars is blue, not red. The red color is a thin oxidized layer. You could brush it off. And underneath, everywhere we've drilled many holes now, well, it depends on how you do colors, but bluish grayish. That red color is a very thin level. Now, all those instruments I talked about, we hit it with everything we had. This was trying every instrument out. X-ray mineralogy, all the isotopes, everything. Looking for carbon, and we found some, and all sorts of stuff. And what we found was the water in the environment which these minerals were deposited in form, you could drink. And everything you could ask for life in terms of an energy source, mineral composition, salinity, etc., was found here. That is, we could check off our list. We found clearly a habitable environment. We're not claiming we found things swimming around, but we found an environment. So that's encouraging. But as soon as we did that, people said, well, how long was that environment there? What climatic record was it? So we go back to the geomorphology. That's where we just were. This is the alluvial fan. There's the catchment. Now, how do I determine how much water it took to make a fan? Again, I appeal to you. I've never found a paper about Earth that asks that question. How much water does it take to make a fan? And how do you do that problem? Well, you could go the really nerdy route and do a bunch of calculations and get Meyer-Peter and try to do intermittency and all this sort of stuff, and you'd burst into tears thinking about all the assumptions. The alternative, which is just one, is to go to the world's record of the ratio of sediment to water load. This is all the channels reported by Savitsky on the planet. This is a distribution function in log space. And say, well, that's the rock to water ratio in rivers. So what I can now do is measure the volume of the fan and divide that into this ratio into the fan, and I get the volume of water needed to make that fan. And if I do that, and then I divide that volume by the drainage area, well, there's the total volume, 4,100 cubic kilometers of water, or if I spread it out, nearly 4 kilometers of water is needed to make that fan. This is very disturbing, because it wasn't a 4-kilometer pile of ice up there. This implies a hydrologic cycle, that there was precipitation of some kind, melting, deposition, evaporation, and return over some time scale. This is not something the climate scientists can yet produce here. But this does not stand alone. And this is the Eberswalder Delta with same calculation, 1 to 10 kilometers, and farther across Mars, another fan, 3.6 kilometers. So in this period, it seems that there is a need for a hydrologic cycle to occur. And the amount of sediment says that. Okay, let's turn our attention to Mount Sharp. I hope to many of you this looks really familiar. This is not the American Southwest, so this is Mount Sharp on Mars. And we're going to head along this roughly now. We've got about 13 kilometers. And here are the gravel stops along the way. This was actually close to where we just drilled. Individual grain amongst sand, but you can see them spread out along there. This is an exposure, overexposed as it's projected, but 100 millimeter scale, so you can see the gravel outcrop there. And here's another example where you can see the stones, individual stones. Poorly sorted gravels, often the median grain size is sort of 10 millimeters, but sometimes getting up to a median grain size of 20 to 30 millimeters. Usually the outcrop is about that. There's not a lot of it, it's crumbly, but it's there along the way. But we also see this, beautiful, beautiful crossbeds, large-scale features, clearly of fluvial sand-bedded origin, but this was a surprise. As we headed toward Mount Sharp, we encountered this. These are rhythmically bedded, thin beds, fine-grained material that are best interpreted as lake sediments. So we drove toward Mount Sharp and got lake sediments, and the interpretation presented by John Grossinger at AGU last fall, so I can show this picture, and will be presented in this picture won't be there, but a publication end of this month by Grossinger and others interprets it this way. This is the rim of Mount Sharp, And so the transport system, we're driving down this transport system across sand and gravel to lake sediments. And the idea then is there was an advancing fluvial deltaic system toward the center of the crater early on in building the base of Mount Sharp. Okay, well, what can we say about this, again, the size of material, the kinds of flows that did this work? How big were the streams? What sort of discharge? Well, in estimating paleoflows and channels, here's an example of an inverted channel in Utah, so you can see what we're talking about. And here's Peace Valley's fan, where there's something like 25 mappable individual channels along here. This one right here is 3 kilometers long. And they're about 25 meters across. So we have evidence of channels. Can we calculate anything from this, a discharge, to get a handle on what sort of flows we're talking about? Well, this is what I put in the paper, so I'm not going to pound your head with this, although these are much simpler equations than some we've seen. We have to write, discharge equal velocity, width times depth. So how am I going to get each of those terms? We can rely on this as a definition of U star, but then we realize that when you want to go to friction, or here, there's g to the 1/2, and that's why you get this sort of velocity correction of about 0.62. Here's one frictional relationship that I've tried out because it's been fit to a lot of coarse-bedded river data that Rob Ferguson put together several years ago. So if I also can point out to you the critical Shields number, gravity cancels out. So that's not a concern in initial motion. I go to Mike Lamb's relationship for a slope-dependent critical shear stress. And I can then combine these equations and solve for depth, which shows it varies inversely with slope and linearly with the D84. This is just the bulk density ratio. And I can solve these for velocity and show that it varies as inverse with slope as a 1/2 power of D84 and some other stuff. So I have a way of calculating velocity. This is a repeat of depth, there's velocity, and then if I just bring in width, I can calculate discharge. I've combined all these equations. There's been many calculations like this done on Mars, using some kind of initial motion, critical stress hypothesis, and some kind of friction relationship to end up doing this. No one's ever written all the terms down to see how ugly it is, but that's basically what you end up with. You could do the same thing using law of the wall, if you preferred that, and this is what you get for that form. To do this threshold channel approach for building a paleo channel, you need at least an estimate of grain size and slope to get velocity and width to get discharge. You have to have at least that to go anywhere. And it turns out this is a bit of a challenge. But now the fair question to ask is, I've written this all down, does it work here? So fortunately, last year, 2 groups published data tabulations looking at hydraulic geometry. The first one is Lee et al., the other is Trompish, both 2014. One is about 230 data points, and the other is about 450 data points. And we've exploited that to say, well, I want to use this on Mars. It should work on Earth if I'm going to do this hyper-empirical approach. So here's an attempt at that. This is predicted velocity depth. I took width out because, of course, I'm going to put that as an observation. I can't invent width. So this is from Lee et al., and you can see the performance is not spectacular. You're sort of okay here, but you're not so great down there. If I move up to discharge, where I'm multiplying width on both sides, the data look a little better, but you can see that this is using all 711 data points. And by the way, this is somehow or another will be available to you on a spreadsheet. The line, this is the one-to-one line, and it's systematically off. But it sort of goes through the data. So this might be, as they might say, good enough for Mars. Let's go a little farther. Hydraulic geometry then. Lee proposed that they found a correlation between U star, the square root, at bank full, square root of boundary shear stress, and slope and viscosity, no grain size dependency. And they emphasized viscosity as being important here. That presents a challenge because what is the viscosity of the water? We have to know its temperature. What was the temperature there? Was it really cold or was it really saline? We're not sure. But we'll proceed as if it was on Earth because we're going to test this on Earth. Well, if you take that assumption, you can solve for the depth relationship and you can use the law of the wall. You can get a velocity relationship and you get a discharge relationship. Look at the difference in the depth dependencies though. This one says it goes each goes inversely as slope, but this one goes as viscosity and that one goes as D84. It's a very different empiricism. Now, this is using the Lee et al. Data, using their expression and saying, do the data points follow in one-to-one line? The answer says it's residual. So it's not a perfect fit to their own data. Here's a hard test of predicted and observed discharge, and, well, it's pretty ugly. Here is discharge, where it should look a little nicer because I've multiplied bankful width on both sides, and it looks pretty good, you have to say, although it doesn't work on steep channels. And a lot of channels on Mars are in this category, so that's a little frustrating. Now I'm going to say something that may surprise you. If you can measure the width, don't bother with all this, use this. That's by far the best relationship. This is all 700 related data points. It's an R squared of 0.9, and the variance is less than anything else we can do, as far as I can tell, trying to use physics and hydraulic equations and things like that. It's just really a nice thing about our solar system, I hope, that we can go from width to discharge and get an estimate, therefore, of discharge. And so in the system I showed you previously, these are about 15 to so meters across. I can estimate that the discharge there was about 18 cubic meters per second, a useful number. Now, but here's the problem I now face. I don't have width. We have not seen anything to give us width in our journey now 3 years. We really don't know depth. We know it's not super deep, but we really don't know depth. All I have is grain size. Now, think about that. If I said to you, this is the size of gravel I have found on Mars, what was the size of the river and its discharge? You might rightly say, go away. No. Well, but unfortunately, you can't do that on Mars because that's all you've got. So you have to do something. And here's what I did. Forgive me. I plotted slope against median grain size. Yeah, the sand's over here and the gravel's over there, and that relationship is due to those big differences between sand and gravel, but there is a relationship there. This is for the Lee et al. Data. The separate data, Trompish et al. Also shows a relationship. Well, if I know, if I can go from grain size to slope with some pretty broad range, I can go from slope to depth. And I can go from slope to width. And I can go from slope to discharge. So if I can get slope with all these uncertainties, I can then estimate that on this gravel here, if I say I really don't know slope at all, and I don't know depth, here's the grain sizes. I would get a depth of about 0.6 to 2.1, a width of 10 to 50 meters, and a velocity of 0.9 meters per second, and that's my discharge. You wouldn't want that uncertainty when you're designing a bridge, but it's not bad for Mars, right? Going from nothing to something. And I'll point out that it turns out that the width of these channels here are about 27 meters, so it falls in the category. Okay, so we go back to this, we can somewhat meaningfully get an idea that we had channels of 10 to 50 meters across. They were probably, order a meter deep, transporting sediment from the uplands up there. So let me conclude with, there is abundant evidence of geomorphic evidence obtained from satellite imagery for the past periods, up to about 3 billion years ago, on Mars, where there must have been a hydrologic cycle. I think that the geomorphology demands that. The discovery of fluvial gravel by the rover adds strong support to the decades of research proposing fluvial activity on Mars. When we drove from our landing spot to the fan, I had colleagues saying, those are lava lakes. Seriously, those are ash flows. And I almost got an ulcer because, I was saying, we're going to go find lake sediments. And fortunately, we and others said that it could be there, and it was there. Topographic data revealed a geomorphic setting that successfully predicted the currents of lakes, which were habitable. The volume of alluvial fans on Mars implies kilometers of runoff needed to make observed fans. This offers quantitative support for wet climate at times. There has to be a hydrologic cycle in that early time of Mars. Stream discharge can be estimated using the threshold channel concept if width of observed discharge is estimated with the least error. So strangely enough, if you give me width, I can give you discharge. And then finally, if only grain size is known, the channel geometry and bankful discharge can be estimated using a correlation of slope with grain size and then slope with all the other things. And so This is where we stand on trying to using geomorphology to estimate water flux and then put constraints on the climate history of Mars. Thank you. Oh.
Well, Bill sort of rambled on, but I'm sure you'd have lynched me if I hadn't let him do so. Thanks, Bill. That's tremendous. So don't go away. And Walter, come back. You can't hide. And the floor is open. Yeah.
Peter Nelson, Colorado State. If you'll allow me, I have questions for each of you. It's not the same question because these aren't exactly similar systems.
There's no wood on Mars.
So I'll start with Walter. I thought that was a really cool talk, and I had a question about the wood transport model. It seems that what you were showing is, and I might be wrong, but what you were showing, it seems like there's not really a feedback at the moment between the wood and the flow. Not necessarily like biological feedbacks, I know that's a whole other can of worms, but between the wood and the flow, has there been any effort made perhaps towards being able to predict wood jams that then cause a backwater effect on the flow field and that kind of stuff?
Thanks for the question. Actually, I forgot to mention, also the wood model has the two-way effect. So the wood is affecting the flow in terms of roughness. So yeah, if there is a bridge and the wood blocks the bridge, you have a backwater effect. And this is what has been measured with the model.
Okay, cool. Thanks. And Bill, so you asked the question, how much water does it take to make a fan? And that was motivated by the people asking you, how long was there water? So what, I understand that you're arguing for a hydrologic cycle, but then how do you go from that inference to some sort of time scale?
I purposely dodged that one. That's I think the hardest one, because you have to decide whether how you bunch up the water. So maybe the scalable channels start to give you a sense of that. And when you try to take the 4 kilometers of water and you say, well, what would be a possible runoff rate? When others have done is they take a snowmelt rate and say, what's the maximum snowmelt rate I can get? And then try to see how much you might, if you had a daily cycle of that. And all I can say is that the numbers range from at least 100 years up to 10,000 to 100,000 years. It's that kind of like, I'm not sure yet. Because the problem of what you all put in your model is intermittency. We were hoping we'd see some stratigraphic break that suggests a hiatus. People were looking for, say, dune deposits that had then a recurring lake on top. We didn't see that. So when you offer yourself the range of possibilities, I think people are comfortable sort of the 1,000 to 10,000, but it could be millions. It could be that there was a period of runoff and then it stopped for a long time. This wet period I talked about, that's the sort of narrow period, if you take away the point and do it in terms of years, it's 200 million years that we have where this could be going on. The way we do aging on Mars, where the community does it, is by crater counts. And we export the rate and size from Mars and correct for atmospheres and then count craters anywhere on Mars. And if you get a large enough area, the number is probably okay. If you count all the craters on the floor and walls of Gale Crater, it suggests that between impact and when things probably shut down could be as little as 200 million years. Little, but that's a long time. So we are comfortable, as you can see, in that range. It certainly wasn't 100 days, and it wasn't 100 years, I think. I think you're in the thousands to anything after that, depending on how you deal with intermittency problems.
So Bill, on Earth we usually have gravel-bedded rivers and sand-bedded rivers, and I'm wondering, do you see evidence for there being deposits that are one kind or the other? I'm wondering whether there's transitions potentially between the two. And the other thing I was wondering is, we have this absence of channels that have a median grain size in the range of about 5 millimeters or something like that. And so if you take those relations and you split them so you only have gravel, do all the relations still hold up? So if you exclude the sand from earth channels, if you have a bimodal distribution of channel types, one's sandy, one's gravel, if you get rid of the sand channels, do you still get all of those relations?
Okay, yeah, I think I know what you're saying. I just blindly took the D50, right, that was in the column. And I'm not aware of the availability of the full grain size on those data sets, so I don't know the answer to how much sand's in those things. It's a fair question to ask. And then going toward the comment about bed material type, we've not seen anything that would be a sand-bedded channel in Gale that we know of. The slopes, I'm a topaholic, so we push very hard to get the gradients of things, so we get topographic surface. And the fan itself goes down to 1%, but it doesn't go another 2 orders of magnitude less. The studies that I've read about elsewhere on Mars tend to always arrive in the gravel range. And in fact, the assumption was before it landed, the sort of international handshake was, let's assume the D50 on Mars is 100 millimeters. Seriously. So there may well be sand systems up there, but they may have been blown away. We see the gravel because they hang around. So I don't know, I have not seen the sand system, put it that way. I've seen a gravel dominance. I think you had something about 5 millimeters in there, but I forgot what the question was.
Yeah, so if you look at like the Tampush, I think it's
Trumpish, I don't know.
Trumpush.
I don't know him.
I don't know.
Somebody know him.
But so there's if you look at the distribution of bankful channels that they looked at,
Yeah.
you have a bimodal distribution of the channel types, a sand type and then a gravel type.
Yes, they all looked at sand, but Lee also looked at sand and gravel too, right? Because
Yeah.
their focus was in the end on sand.
Yeah, so all the data sets seem
Yeah.
to show that. So
Yeah.
then I'm just wondering, so when you draw those lines, you're using the sand channels and the gravel
Yes.
channels in your
Oh,
line
yeah,
fits.
I
And
meant-
so if you just look at the gravel channels, I wonder whether they hold up.
Oh yeah, no, I'm sorry. I'm sorry. I did a bigger blink and nod than you didn't catch or did catch. I acknowledge that the reason this looks as good as it does, if you're going to call it that, is because I'm going from sand to gravel. I did say that, but I probably didn't say it enough. And if I only looked at gravel, it's just looks like someone shot it with a gun. I understand that. That's where we are, right? I understand that. Yeah.
Gordon Grant.
Both of you very, very fine ending talks for this meeting. This is the bill. I anticipate an internal chuckle as I ask it, but I nonetheless wonder if you have calculated your fruit numbers for your sort of fields. Not as in a deterministic way, but certainly as a constraint, I would expect, and we just have done a re-review of this, if you were to find that your predictions, say, put you up into the supercritical regime, I would be rather suspicious of your numbers, at least using analogy for rivers here on Earth. And in fact, it would be interesting to see how close to critical they come, because that does seem to be a characteristic of steep enough gravel bed rivers on Earth.
Right. Well, in Marissa Pelusa's paper, she actually explicitly explores the fruit number idea and says, because the review that John Stock did of fans says what limited data there are is that there's a tendency to be close to a fruit number of 1. So she actually uses that as a constraint in a completely different way than I've done here. Not using Earth data at all to say, well, if the fruit number is 1 and I have this estimate, she has an estimate of width and a crude estimate of depth, then it kind of works. So on the fan, I think that's possible. But on the stuff we're driving across now, I just can't tell. I mean, I'm reluctant to. All I've got is grain size, so I haven't attempted to wrestle with that beast because there just isn't anything to guide me. But on the fan, I think the fruit number 1 is probably not probably a useful exploration.
Thank you. Michael Attal from Edinburgh. I've got a question for you both, and it's about seasons. So I always assumed that the cyclicity in lake sediment was due to seasons. So do you think that there had been seasons on Mars? And well, maybe that first one.
Yes.
Okay, thank you. That was easy. And the second is
really
for...
is seasons, so it is quite possible. Yeah.
Okay, right. And the second is for Walter. I had a colleague who was looking at the vegetation recovery following a volcanic eruption in Iceland, and they saw that there was a strong season effect. If the eruption happened in winter, the vegetation would struggle to recover compared to if it happened in spring, for example. So do you think that you can have similar effect in your rivers if the big floods happen preferentially in winter?
Well, definitely. If you want to reproduce the evolution of a river, I think looking at vegetation as well, you need to take into account seasons. Because of vegetation growth, so vegetation can grow in different way in winter or in summer, but also the impact on roughness can be different. So particularly if your species are broadleaf species, of course the roughness during summer is much higher than the roughness during winter, so you have to take this into account.
Colin? Colin, go on.
Again, if we're allowed 2 questions, they're quite short. Bill, could you put back up your final width equation, which is...
My final width equation?
Yeah, your width discharge equation for Mars. It's
right.
Q equals 0.2
yeah.
W to the 1.66.
Yeah, that one?
Yeah, I like that a lot. And as a former Colorado State professor, we love to see those log graphs. You can build a whole dynasty on. And it's really, really helpful. I mean, everybody who does hydraulic geometry knows the width is the one you hang your hat on, and the slope is really, really iffy. And I would probably believe in a solar system-wide width discharge relation too. I'm not sure how many people in the room would, but I wouldn't expect 1.66 as the exponent. I'd be looking for something closer to 0.5. And okay. So what? Okay. So what do you get if you do width as a function of discharge? Of course you do. Oh, thank goodness for that. Sorry. Yeah. It is putting your hat on differently. I forgot to say one thing though. To take this to Mars, I have to correct the discharge by the 0.6 velocity. Yeah. Okay. So then the follow-up question is, the thing I've got reamed out for more than anything else about hydraulic geometry is it's only for regime-adjusted channels. Looking at your wonderful images, satellite images, those channels look a bit incised to me, like they've cut into the delta. They didn't build it. They've trenched into it a little bit. And I just wonder if you thought about some kind of Martian channel evolution model, that those are rather late stage delta channels rather than... What image are you talking about? Because most of the things we see are aggradational features. So what image did I show that looked like it was in size? The ones with the channels that have been mapped, the discontinuous ones. Those are all inverted. Ah, okay. Yeah, they stand about 5 meters high. Okay. Sorry, I didn't make that clear. Yeah, so they built the fan. Right, so they're not depressions. No, they're ridges. Yeah. That. Okay. I apologize. Sorry. I didn't pick that up.
I think you'd better quit, Colin, while you're behind.
Okay. And just one for Walter. In terms of modeling vegetation effects of a bit longer time, isn't it more about the succession rather than the success of the pioneer species?
Yes, of course. Well, going back to my first slide, all models are on approximation, and it really depends on what you are looking at. The model that I showed you, it's more on a short time scale, so a few years, let's say. If you are interested in longer time scales, yes, you need to include succession of species, and this can be relevant. But this has been done also by other models. But usually they do not take into account morphology, morphological changes. And I think one of the big questions now is to couple morphological evolution and vegetation succession on long time scale.
Joel Johnson.
Hi, Joel Johnson here. Bill, you showed kind of well-sorted, relatively tight distributions of grain sizes. Is there longitudinal sorting in this system? Meaning, the rover is driven around, decent distances. It wasn't entirely clear how much it's moved kind of distally versus proximally, but, is there spatial sorting that you've observed?
We're working on that right now. I've looked at every single image, and we're plotting. There's colleagues at Davis are doing the grain size analysis, and then we're placing that in a topographic sedentological framework. Visual impression is not much, but it's a good question.
Obviously, it seems like it could give you another big constraint.
No, we're trying to. The thing about the fluvial gravels is they're fluvial, whereas some of the sand material, there's reasonable arm wrestling how much is aeolian and how much is fluvial. So I've sort of tried to pick on the gravel to get as much information we can out of them.
John Laurent.
Hi, Bill. I like the shoe and the table. But I think that if a Martian was here, he wouldn't necessarily agree with us that a shoe is a shoe, because the conditions are different. And so could you please show again the one figure that is most interesting, I think, and that is where you show the gravel?
The very first time, that one?
I think so.
Go back to here?
Yes.
Okay.
I think that is a very interesting photograph, and I think it shows us anywhere between some particles that are rounded to many particles that are slightly rounded to some particles that are not. And we know that there's quite a lot of aeolian activity, so that sand, blasting, whatever can do things, especially over very long periods of time. Have you taken any of this into consideration?
That was definitely part of the debate. And so if you can, we've had, because of the way that this particular outcrop, which is cemented, stands out, you can actually go and interrogate a lot of the rocks there. And you can see that you can get a sense of the rounding that's in place rounding, not altered by wind erosion. So but the issue of wind abrasion and how it affects rocks is something that we've had quite a bit of debate, because in the low atmosphere of Mars, the collisions are quite intense. And the particles up to several millimeters, maybe we've had my colleagues say maybe up to 3 or 4 millimeters could actually creep along from impact, not wind, but being bounced along. But this was important. These grain sizes are bigger than anyone has been able to argue would be wind transported. And then, which I don't think you were suggesting, you're basically suggesting some of the attributes post-deposit rounding. Is that what you're suggesting? Yeah. And I would say the key component is that, well, it's hard to show all the pictures, but looking close up in place, you see the rounding very well defined. But I want to say it's not perfect rounding, and you're right, the median, the power scale is probably 3.5 or something like that, not 6 in terms of rounding. So, but the other thing that I thought you were going to say is, well, how far did it travel? And we think we know where this came from, because we can actually, I didn't say this, but the fan, Peace Valley's fan, has a definable volume, and Marissa Pelousas was able to show that it came from a gully system that we could identify. And the gully was cut into post-impact colluvium and dust and stuff. And the travel distance for this would be order 10, 20 kilometers. Doug Jerelmack has worked recently and has a theoretical paper out last year and one coming out where he feels he can actually get even more information about grain shape and travel distance. I haven't seen the paper, I've heard about it through the grapevine. So I think there's more information than to come on the interpreting the grain size, but I think that we can address the wind abrasion as not being a primary effect on the shape of these grains.
Thank you. Bill, if you look at hydraulic geometry on the Earth, and in addition to fluvial systems, if you consider debris flows and hyperconcentrated flows, you'll find an almost identical exponent for the relation, but a different coefficient. The channels are wider. So have you thought about evidence of fluvial versus hyperconcentrated and debris flows?
Yeah, almost every image we've seen has a sorting characteristics of grain contact and sometimes some level of stratigraphy. There's one spot we've found that looks like it could be matrix supported, but there's high-rise images of where we're headed, which for lack of a better term we're calling the entrance canyon, that the rocks are big enough that they're boulders the size of these tables that we can see, and they're scattered through the deposit. And they're in a deposit on a fan that's about 12 degrees, and I'm quite convinced they're debris flow deposits. And so there definitely are debris flow deposits in the system. And again, it seems like the slope process dominant relationship holds there with the bigger rocks and the poorer sorting in the steeper systems.
And I guess I didn't say this, but what I was getting at is that the channel geometry may be very dependent on the rheology.
Yes.
And then so getting that straight is important for this.
Yeah. Agreed.
Extraterrestrial.
So when we came, we were at the base of the fan of a 1% or 1 degree, get this right, 1% slope, sorry, 1.5% slope in Peace Vallis. We don't anticipate significant debris flow activity down there. Near the head, though, we found inverted channels with some boulders in it. And then everything that we've driven across so far, heading away from there and heading toward Mount Sharp, is we don't see any evidence for matrix supported, so that's why I haven't attempted to think about, to try to segregate out what a different hydraulic geometry would be for debris flow dominant. But I take your point, it's a good one.
Next? Well, I guess we're just out of time. So I'm going to thank Walter for a really interesting exposition of wood and vegetation, and Bill for a remarkable exposition of no wood and no vegetation. Definitely a left-skewed discussion. Thanks, both.